Let me just give you a brief thing. And these are what you call as a ABX3 crystal structure, where your A site is your methylammonium cation, cesium, and formamidium. And it so happened that these are the only three A site cation that goes inside the cavity of this lead halide complex and gives you that perovskite structure. Other cations are either too small, like sodium, potassium, rubidium, or these other ethyl ammonium, those kind of things are larger. So based on that, it forms a structure. So it is very analogous to the oxide perovskites, where it is AbO3, like strontium titanate. But it so happens that here we have a halide ion. And a prototypical compound is like a methylammonium lead iodide that has been widely used. And you can substitute this methylammonium with cesium or formamidium and substitute iodine with bromide or chloride. You can still get these things. And how you make it is the solar cells is you put a this is your conducting glass. It is a FTO glass. Is a large crystallites. On the top of it, you put TiO2 and methylammonium iodide. That's your active layer. And TiO2 is typically an electron transport layer. On the top of it, you put spirometad or any hole conductor and a gold. So you are all set in terms of a solar cell. And again, you can make these kind of a cells shown in your right hand side for testing purposes. And then you connect it to their leads, and then you record your what they call current voltage curves, or you can get the IPCE uh, curves to find out the photon to current generation efficiency. So again, this is just to show you what the solar cell looks like. From there, now people are trying to make perovskite and silicon tandem solar cells. In this one, when you shine the light, the perovskite absorbs the high energy photons and then lets you go to the silicon absorbs the other photons transmitted through. As a result, people have now made over 33% efficient cells in this one. Uh, since I'm talking about photocatalysis, let's move on from photovoltaics to solar fuels. When you talk about solar fuels, there are two processes they stand out. One is trying to generate hydrogen. Hydrogen is going to play a major role in the next 20-25 years as a major energy supplier. Right now, we are not using much hydrogen for any energy purposes, but by 2050, it is expected that 10 to 20% of our energy supply will come from hydrogen. And I'll come back in a minute how we are going to produce hydrogen using renewable energy. There is also another field that is emerging is reducing CO2 to get valuable value-added chemicals, for example, fuels like methanol, ethanol, so or methane, CO. So all these things, there is an other studies. Uh, Again, there have been a lot of designs you might have seen in the papers, like a Z scheme or putting a metal particles, putting on a graphene, tandem structures to make especially this hydrogen generation in photocatalysis. Another way you can also do is attach like a perovskite solar cell to an existing photocatalytic system. So here it is a bismuth vanadate that is a photoanode, and there is a platinum, and this is biased by this perovskite solar cell that holds a certain positive potential at bismuth vanadate. And when you shine the light, the high energy photons are absorbed by bismuth vanadate, and the low energy photons are transmitted, absorbed by perovskite, and that gives you bias, and you can generate oxygen and hydrogen using this electrolysis. This is just one of the concepts we showed earlier to do with a water electrolysis. I was telling you that how it can be done is simple electrolysis. So what you need is two electrodes and water to generate hydrogen and oxygen. And one of the things people use is solar cells, the photovoltaics. And then you can drive that one, you can make hydrogen and oxygen. And this is a pilot plant in California that was established by Honda. But there are more serious efforts globally. For example, in Denmark, there is a large consortium called Power to X, and they have a lot of wind energy, and they don't know what to do with the excess energy. So as a result, they are putting these electrolysis plants to create uh, uh, this one hydrogen, and so you can use it the hydrogen for any industrial reductant or also as a fuel. Here is another example to show you from Japan, where there is a solar farm combined with a hydrogen generating electrolysis plant. So these are realistically happening right now around the world, and we have to see how we have to do it. Uh, so now coming back to this perovskite, that was just to give you an idea about how the hydrogen and solar fuels. The perovskite nanocrystals can be effective photocatalysis. It is the same hot injection method as made for cadmium selenide, and that one you have it here. It's a chloride, cesium lead chloride, cesium lead bromide, iodide, and it's a manganese doped cesium lead chloride. And as you can see here, you can tune their band gap based on the halide composition or this manganese dopant.
Sir, we can't hear you.
You don't need to go and look for a different type of material. So these are some oxides, metal chalcogenides, and other things. We have a different band gap. So you need a conduction band greater than the hydrogen reduction potential, and valence band more than oxygen generation, that is minus, sorry, 1.23 volts, right? So unfortunately, most of semiconductor, either they can do reduction or oxidation. So as a result, people have started combining those things. But here in metal halide perovskite, very similar situation, but people wanted to explore how they have done in these things. So with that one, we wanted to study these photocatalytic aspects of perovskite nanocrystals. And if you look into the literature, this early work showed that you can split hydrogen iodide to generate uh, to generate hydrogen to do it. And the iodide, which is here, it repairs these perovskite nanocrystals. There is also people have used for reducing CO2 or making some chemicals. And this is one of our colleague at Notre Dame did, was trying to polymerize by a photocatalytic method. So they substituted these ligands with these monomers of methacrylate, and then you shine light with 420 nanometers, and that led to this photopolymerization. And then this one is stable even in polar media. So I'm coming back to that one a little later. Again, I told you about these ones doing hydrogen reduction, sorry, hydrogen generation. That means H plus getting reduced to H2. But it's very difficult to probe what happens at the surface. So in order to probe these electron transfer processes, we use viologens just to have a reduction of these viologens in this one. So again, I will show you some of the results related to this reduction. One of the things, first thing we do is take an emission spectrum. I told you that cesium lead bromide, for example, gives a bright green emission, and that's around 510, 520 nanometers. And when you add this viologen in a very low concentrations, up to even micromolar, you can see a complete quenching of this emission. That means we are losing those electrons to viologen to give you this one. So we can treat this one as an equilibrium between methyl viologen and cesium lead bromide and get an expression, what you call a double reciprocal plot. And from this plot, we can calculate the association constant. And typically, these are of the order of 10 raised to 6 inverse molar. And that basically tells you that even when you add a micromolar concentration, we get everything bound to the surface of these nanocrystals. So in that, I will give you more details, but what we found out was the electron that goes in here to the viologen, it becomes part of this whole system, and it still communicates with the cesium lead holes remaining in cesium lead bromide. As a result, we see a very long-lived charge carrier separation. And we can also record the viologen radical formation and how long it is lived. So that is sort of a thing so happening. But before I move, there is a question is, there are a lot of problems with these perovskite nanocrystals. So if you ever work with most of it, as I said, you want to use it in water to split, make hydrogen. But these are having problem. For example, if you add any polar medium, these are nanoplatelets of the cesium lead bromide, and even few percentage, 1 to 2% of acetonitrile, when you add, the structure deforms and forms these larger crystals. And you can see here the emission quenching and a new emission forming down here as it is a bigger crystal. So some of these are very sensitive to the polar solvents, and we can show that the more polar it is, the stability goes down in the solvent. So that is one problem. The second problem is when you add excess ligand, like in this case, this DDAB ligand, when we add, actually it becomes 2D perovskite. From 3D perovskite, we get 2D perovskite. So again, another problem. The third one is the exchange. So if you have take cesium lead bromide, and you can even throw in a iodide, potassium iodide crystal, and you will see the shift from bromide to iodide. So in this experiment, what we did was we mixed cesium lead bromide, which has absorption around 500 nanometers, and cesium lead iodide, which has absorption just below 700 nanometers. So as they go, the iodide and bromide, they exchange between the two particles, and what you are getting is a mixed halide particle. So that means each one has both bromide and iodide. You can also follow the emission. This is the bromide emission, this is the iodide emission. With time, you can see here in 300 minutes, they all became same. So here it is, this is a bromide, and when you add iodide, you can see the change in the color of the emission as they exchange ions. So again, this is showing you the absorbance, how it changes in a film. So very similar things happen. So this is another problem with it. The last one is when you want to make a metal particles, because typically what one wants to do is on a semiconductor nanoparticle, people put a small deposit of metal particle. It's either gold or platinum. So the idea is that they serve as electron acceptors and catalyze the reduction process. When we try to do gold, we added gold bromide to the cesium lead bromide. You see very small particles forming at the corner of this cesium lead bromide. But when you shine the light, what happens is they all come out, get dislocated from the each side, and then they form a cluster of small particles. And if you continue further, all of them, they form this large cluster of gold particles. So essentially, the gold that is deposited on this cesium lead bromide is not stable. So if you look into the literature, there is not much studies or people have succeeded in putting metal particles on the cesium lead bromide, and for the same reason, It is highly unstable under those situations. Another one is the reversible cation exchange. So that means if you add a excess of gold bromide to the cesium lead bromide, it kicks out lead from it and forms these what we call double halide perovskites, CS2A to Br6, and that is dark color. And it is a reversible. So you add excess PbBr2, it comes back the original one. So this is showing. So basically, I told you some of the problems that we encountered in trying to make use of the catalyst. So once you identify it, now we have to make it working. So one thing we sought was a capping with a nanocrystal with a shell. And there are some reports, people putting this polymer shell. Uh, Again, this is another polymerization using this PMA. And some people have even succeeded in putting a silica shell around it. So in order to protect from the solvent or the chemicals or any other transformation, so that one can use these things. Here is what we did. So we took this cesium lead bromide, and in a two-step process, we deposited a thin layer of cadmium sulfide. And we checked the zeta potential change, that making sure it has happened. We have this elemental analysis to show that we do have a cadmium and sulfide on the surface. We recovered absorption and emission spectra. All of them concluded that we do have a CDS shell and it protected it. For example, if you put 15% ethanol without the shell, you almost quench the fluorescence. Whereas here you see an initial decrease of about 20%, but then remains same. You can also electrophoretically deposit in terms of films of these CDS capped cesium lead bromide nanocrystals. We wanted to study electron transfer reactions, and again we use the viologen. This is the ethyl viologen, and essentially now the electron tunnels through this CDS to reduce this one. We use small amounts of ethanol to take away the holes so that only reduction process is favored. So if you can see here in this graph, uh, when you shine the light of this one, viologen, and this your CDS cap cesium bromide in say 15% ethanol and 85% toluene, we see the formation of viologen radical. That is an electron transfer product. So this is how we can probe this electron transfer process. So you can see the absorbance, which is proportional to the concentration of the electron transfer product, is increases with time of irradiation. We can also use the information on how much reduction product, that is the radical that's formed, viologen radical, and so you can calculate what we call flat band potential or Fermi level of this system. So moving forward, we also used this methyl methacrylate, polymethyl methacrylate capped the CDS, cesium lead bromide nanocrystals for reduction purpose. So here you can see here we increase the ethanol concentration. There is initial decrease, but later on it didn't make any difference. So even here it is stable in water, but the only problem is it is not suspendable. So these kind of now systems, nanocrystals, if protected properly, one can use it in a polar medium for photocatalysis. So we did some transient absorption experiments in which we basically record absorption following the laser pulse excitation. So if you don't have any viologen, so you have this charge separation, you see this intense bleach, which is disappearance of the excitonic band as these charge carriers are formed, electron and holes. And when you add this viologen, say here, you see this electron going in here to the viologen. That means there is no emission coming up and they don't recombine. And what we see is a fast decay, but there is a residual bleach. And if you look into this carefully, the black one, which is the first one here, you see this fast recovery, and that is because of this charge carrier recombination. Now you start adding small amounts of viologen and record the same kinetics, that is how fast this one decays. You see a fast decay, but the residual one. With increasing this one concentration of viologen, this residual bleach increases. So this one is telling us that this is what the electron transfer occurred, and there's a holes are still remaining in the uh, uh, cesium lead bromide nanocrystals. We can also look into the 605 nanometers. I showed you earlier that here this is a very characteristic absorption of viologen. So now we can go back at 605 nanometers. Again, you can see here there is a small absorption. This one is found very fast. Within about 5 picoseconds, this electron transfer occurs. Uh, we can also study back electron transfer. That means whatever that is produced here, viologen, can give back this electron to these holes, and that one you follow by following the long-term recovery. So now from picoseconds we are moving into the nanoseconds time scale. Here this is 1000 nanosecond or a 1 microsecond time scale, they recover back. If you look in 605 nanometers, we see the same behavior, that it decays, but a small fraction that escapes this shell, and then it stabilizes down here, and that's what we are looking for, and that's when we do the steady state photolysis. And in the steady state photolysis, this viologen radical is formed, and so you can see follow the growth of this viologen radical as it's formed here, and then it start decaying back. So when you turn it off, there is again a back electron transfer, and so that's sort of a thing. It decays back, and we can use a steady state expression to calculate the forward rate and a back electron rate, and using the values that we can determine from this is the viologen radical concentration, and we can calculate a back electron transfer rate constant from this exercise. And again, using these values, you can also calculate the forward electron transfer rate. To summarize, what I have been telling you is when you take this semiconductor nanocrystal in a viologen system, excite with a, we see a very fast electron transfer of the order of 10 to the 11. And then that one forms this bound cation radical. In 1 second. And some of this reduced cation either escapes or hops to get stabilized to form a free cation radical. And that's the rate constant for that process. And this one can also back electron transfer with a much slower rate compared to this one, and then this is what we get. So this sort of it shows you a cycle of how electron transfer and a back electron transfer occurs in the semiconductor photocatalytic system. And the key thing to maximize this yield is to get this back electron transfer as low as possible, which means they don't not near the surface of this semiconductor nanocrystal. So here are some other values. You have got the net electron transfer efficiencies, and those things you can calculate. So I'm going to how much? Yeah. So my time is up. So half an hour. So this is sort of a summary. I wanted to give a short glimpse of photocatalytic reaction and how it is being probed using transient absorption spectroscopy. And they are still very active research. People using it convert light energy into chemical energy, and there is a uh, need to improve or control these various electron transfer paths, so maximize the yield of this one. So that's our current group of students in our group. So they are the one who make it possible. And so with that, I would like to thank uh, all of you for giving me this opportunity to present this talk. Thank you very much.
Now this session is open for discussions.
Morning, sir. Thank you for your wonderful talk. I have some basic questions like you showed from chloride to bromide to iodide. As you go,
Yeah,
the band gap keep decreasing. So
yeah,
there was a slide which shows that the valence band is going up and conduction band remains the same. So
yeah.
is it characterized like that? The
Yeah, no, yeah, the reason is the conduction band is dictated by the lead. The lead, because lead is common, that's why conduction band remains same. Whereas your uh, valence band is dictated by the chloride, halide ions.
okay,
So, as you may know, iodide is much easier to oxidize than bromide, and bromide is easier than this one. So, if you do a cyclic voltammetry, you will know it. So, as a result, their valence band is the one that is shifts, whereas the conduction band is considered as a isoenergetic. So, there is a small difference, but not much.
yes, sir. Another question was you replace lead with silver. So it becomes Ag2I3. CSPbI3 goes to CsAg2I3. So this two silver metals will be substituting not in the lead position, right? So lead sits in the octahedron, center of the octahedron.
Yeah, yeah. See, that is you get a totally different structure, what they call as a double halide perovskite. In that one, see, as you know, lead is divalent, Pb2 plus, right? And gold, when it's there, is 3 plus. So what happens is gold 3 also changes into gold 1. So alternate between 3 and 1, they balance the charge. So people have done with say bismuth and silver too. Like bismuth is 3 and silver is 1. So these are called double halide perovskite. So they have alternate structures. So people thought it was a good one to make it because you can make non lead based material. But so far, these kind of materials are not very photoactive. So you can try it. You can make a cesium lead bromide nanocrystals and just add some gold bromide, and it will right away exchange, and you get a dark colored solution. And if to that one, if you had a lead bromide, it reverts back because it kicks out, and it is an metal ion exchange, but it is a different structure than original structure.
Yes, sir, but this metal still sits in the center of the octahedron, is it? Or is it
It
outside in
is,
the
yeah, I
voids?
think it's mostly remains same, but it is an alternate layer of AU3 plus and AU1 plus.
Okay, sir. Thank you, sir.
Thank you, sir. Thank you for a nice presentation.
Okay.
I have just one doubt. Like you were talking of electrodeposition for making co-shell nanoparticles.
Yeah.
Yeah. Can you suggest some other methods other than
Yeah, like
electrodeposition?
what happens is that was just to show that we did have a shell around our particle. Um, Typically, all nanoparticles have certain charge. Mostly they are negative charge. It's a built-in either with the solvent or with the ligand. So what you do is you put these two electrode in an electric field, and the solvent needs to be like a non-polar. And the reason is because when you pass this high voltage, like anywhere from 50 to 100 DC volt, it creates an electric field. And so the negatively charged particles go towards uh, the positive electrode and get deposited. So, for example, you can make cadmium selenide. But surprisingly, if you make cesium lead bromide, we have tried it with the normal oleamine oleic acid, you cannot electrode deposit. But when you had this CAD sulfide shell, we were able to deposit because the zeta potential became negative and we can do it. So that was the one, just a testing purpose. So we didn't use it for this one, but there is another paper that we published earlier where we made this lead sulfate capped cesium lead bromide, and we could deposit it on the electrode, and then we can use it for, we even made LEDs from those kind of films.
Okay, sir. Thank you.
So did I answer your question?
Yeah,
Yeah,
yeah.
because
Can you-
most of the particle you have to do it, and if you want to have a power supply, you can go to any biochemist. They typically do these electrogel electrophoresis, where they apply electric field to separate out these different large molecules and those things. So it's basically similar principle.
Okay, what about the thickness of the shell, sir? Will it be uniform throughout?
This thickness is very small, it's 1 to 2 nanometers. So we couldn't make it a thicker shell.
Okay, thank you.
Thank you, sir, for your valuable
Okay.
session and
Okay.
inspiring us with your sagacious words. Uh, excuse me, sir, there is one more question.
Okay.
Thank you very much, sir, for your presentation. I want to ask one question. Some time ago, I partake in one research that involved solar cells, that dye synthesized solar cells, where I used some green chemistry, that's green plants. I extracted them, and I used the dye, like of magniferin. I used the dye in increasing the efficiency of solar cells. Now, you still talking about the same solar cells. I remember when I used the dye, then I have a little reasonable amount of efficiency. Now, with this method you have developed, I think there is something unique in it. Can you please use your experienced knowledge to tell me how maybe this can be more effective than just using a green chemistry in increasing the efficiency of solar cells?
Yeah, again, there are two aspects, right? One is you want to have something practical device that can deliver. Another one is thinking about green. Again, there are two school of thoughts, and finally they will merge someday. But right now, for example, your cars that you drive, you have a lead acid battery, right? So theoretically, they are not green, and we have been using it for more than 100 years. Uh, so same way, these lead halide perovskites, they have been giving very high efficiencies. They are coming very close to silicon solar cells. And the idea is it all started with your dye-sensitized solar cell. And dye-sensitized solar cell, you can get anywhere from 12-13%. That's, I think, the highest one that is reported. Then there are organic PVs came in. Then semiconductor quantum dot solar cell came in. They're again still in the range of 12 to 15% range. But this perovskite solar cell can give you anywhere from 24 to 25%. I think the highest recorded is 26%. And so people have moved from those kind of cells into making more of this perovskite solar cell. Having said that, there is a stability issue with the perovskite solar cell. They are not very stable under long-term operation. So that needs to be mitigated, that problem. So it is not the efficiency problem right now. It is trying to keep it more stable under outdoor operations. So again, you can select whatever system you want to do it. My thing is, don't get stuck up with this green chemistry or anything. Try to understand the science or scientific insights into the processes. In that way, you will learn more. So we are all here to learn, okay?
Thank you, sir. Thank you,
Okay.
sir, for your wonderful presentation. I have a doubt. Sir, can you comment on the use of semiconductor quantum dots in photocatalysis and the solar cell application?
Yeah, what is the whole semiconductor photocatalysis is out there more than 40 years. And we have been, again, I'm trying to criticize myself, okay? We have been working for 40 years and we have not solved the problem. And the problem with the particles is such that the electron hole recombination is more predominant. And people try to take one of these charge carriers, like people use sacrificial donors, take away holes, and then they say reduction. Either you can make hydrogen or CO2 reduction, those kind of things. But still, it doesn't really answer the question whether the systems can be really made a practical device. For example, I showed you that example. If you take a electric power and just connect to electrodes, you get a lot of hydrogen and oxygen. For example, we do show a demonstration with two pencils stuck in a beaker and connect to a photovoltaic power supply, and you put it in the sun, you'll see this hydrogen coming out like crazy. Uh, so that is more efficient than the semiconductor particle system. Then you have the issue of stability. So that also needs to be considered. So all these things you consider, the development in solar cell is significantly streamlined. You can make now solar cells with 24% efficiency, 25% efficiencies. So this need to be recognized, and there is also another problem in photocatalysis. Everyone uses their own method, then there is no standard method for photocatalysis. But if you are using solar cell, there are standard methods of characterization. So you have IV curves, you have got IPs, external quantum efficiencies, you have stability. So you need to provide those parameters so that they are all standardized. But in the photocatalysis, whatever I do in my lab and whatever you do in your lab, the conditions are not same. So sometimes comparison becomes very difficult. So that is another hampering thing in this situation. So the photocatalysis is a, but people have learned a lot of scientific insights into these processes and how, and that's what we are looking into, making materials and using it for different purposes. So don't get me wrong, please continue your research if you are working with these particles, but keep in mind that the, making it really a competitive device is very difficult. That's why we don't have any photocatalytic device in the market other than air purification.
Sir, thank you, sir. And one more doubt, in case of cadmium sulfate quantum dots based solar cells, sometimes it is seen that we can dope it with a transition metal. So what happens when a transition metal is doped with these kind of nanoparticles? How it is affecting the band gap and energy?
Yeah, again, that depends upon what we are doping with, what is the concentration. So all these parameters. So there is not one general formula that one can think of to give you the answer. But sometimes it is just a protective layer or transporting. Like if you just put a thin metal layer, like the one we put cadmium sulfide on cesium lead bromide, it just protected it, but it didn't stop the electron flow. So sometimes it is just like that. On the other hand, you can dope some of these semiconductors with other metal ions, like the manganese ions. If you put it in cesium lead bromide, it creates an intermediate stage within the band gap, and it changes the whole energetics. So again, you need to see what you are doping with, what is the concentration, and those kind of things. If you are looking for it, and the ternary semiconductors are interesting, like silver indium sulfide or silver indium selenide, copper indium sulfide, copper indium selenide. There, when you change the ratio of copper to indium or silver to indium, uh, the intermediate states, they change, the energetics change, and you can follow those ones through emission spectra and those kind of a characterization. You need to find a fingerprint or a spectral fingerprint, what happens. And sometimes people do like a UPS uh, to measure the band gap and those kind of a things. So you can do that one too.
Okay, thank you, sir.
Yeah. Okay. Thanks again for giving me the opportunity to talk to you. Okay. Next time I'll come and visit you.
Uh, uh, this is Zina. So thank you, Professor Prashant, for the informative talk. So just had a
Yeah.
couple of questions. As you mentioned about the back electron transfer, so
Yeah.
can it be directly related to the polarity of the solvent, or let's say when we consider a polymer encapsulated, perovskite materials,
Yeah.
so can we draw some general statements like
Yes,
connecting the back
yes.
electron
I
transfer?
think you raise a good point, and the back electron transfers are much easier to study, but people never, or I don't say never, but people put more emphasis on the forward electron transfer, but not so much on the back electron transfer. So, as you know from the steady state, both forward and back electron transfer are important to raise. And what you need to do is the electron transfer product that is formed should move away from the parent nanocrystal or whatever it is. And having this solvent polarity helps, because if it is a solvation cell forms around your product species, that helps you protect and slow down. So for example, the same study I showed you, we can vary the solvent polarity and measure the back electron transfer rate and see how it affects the yield. So we have not done it, but that is one of the easy way to check. Is if you are seeing in a steady state, for example, even say cat sulfide or selenide, when you make it and you put a viologen, and when you do in your steady state photolysis, you will see in the spectrophotometer the peak coming up, and after a certain time, it doesn't increase anymore. That's the steady state. At that time, your forward and back electron transfer, they are same. So you know the how much viologen you have reduced. So you have both concentrations. So based on that, you can calculate forward and back electron transfer. So now repeat this experiment with different solvent polarity, right? So you should be able to do it this way.
Okay, thank you. Thanks a lot.
Yeah.
Any more questions? Any questions from the student side? Once again, thank you, sir, for your valuable session. On behalf of Department of Chemistry and entire Amrita family, I extend my heartiest gratitude uh, for joining us today. Thank you, sir.
Thank you. Thank you again. Yeah. Bye.
Professor Deepti, are you online?
Yes, yes, Dr. Naveen, I'm here.
Okay, okay. You can please turn on the video. Then I think maybe we'll start with the introduction. And
Now, I would like to invite Dr. Shailesh Chandran, MS, Assistant Professor, Department of Chemistry, to introduce our next speaker, Professor Deepti Menon, Amrita Institute of Medical Sciences, Kochi, for the next session. Sir, please come to the dais.
Good morning, everyone. With immense pleasure, ICMSC conference welcomes Professor Deepti Menon, Amrita Center for Nanoscience and Molecular Medicine, Amrita Vishwavidyapeetham. So, Professor Deepti Menon's main research area spans over nanomaterials, bioengineering, drug delivery, cancer diagnosis and therapy, regenerative engineering, etc. And she authored around 80 plus journal publications and several book chapters and holds an H index of around 50 and hold an item index of 99 and have a citation over 10,000. Professor Deepti's doctoral degree is in physics in material science from IIC Bangalore, and his postdoctoral trainings are obtained from Technical University Netherlands, National Cancer Institute of USA, and International School of Photonics, KUSAT. So, Dr. Deepti has received several recognitions in her research career, which includes the prestigious Young Research Award from the International Union of Material Research Society and Young Scientist Fellowship and a Boycast Fellowship from Department of Science and Technology and Rapid Young Investigator Grant from Department of Biotechnology. And we warmly welcome Deepti ma'am for presenting her keynote talk on the topic functional nanobiomaterials for the potential applications in medicine. Welcome, ma'am.
Thank you. Thanks to the Amrita family for inviting me to this presentation at the conference conducted by the Department of Chemistry. I would like to start with an apology. Actually, I was supposed to be present there today, but due to some inconvenience I had a leg sprain the other day and I cannot walk properly. So that's why I have come online. I'm sorry about that. But today, in the given time, I would like to talk to you about the kind of works that we do at Amrita School of Nanosciences and Molecular Medicine at Amrita Institute of Medical Sciences, Kochi. So, a very brief outline of the talk. I'll be introducing you to nano-engineered materials, more so about one-dimensional nanofibrous materials in medicine, and then to nano yarns and nanotextiles, and then to nanoparticles for drug delivery and a few representative case studies. So to introduce the size scale, I don't think I need to spend too long, but just to bridge the gap, I just wanted to say that we are talking about materials whose size scale is within the 10 to 100 nanometer or slightly beyond, maybe 200 nanometers. We are talking about the bottommost level of size. In this particular size scale, we can actually develop varieties of materials, whether it be carbon-based, whether it be polymer-based, whether it's inorganic or organic materials. These materials are what I would like to call as engineered nanomaterials. So, engineered nanomaterials are the ones that are not available in nature. We are designing and integrating the products because of the specific characteristic of the nanomaterial. It is this human origin which is engineered. It can be metals, it can be quantum dots, it can be nanotubes, it can be nano capsules, everything engineered using nanotechnology. These materials can either be zero-dimensional, one-dimensional, two-dimensional, or three-dimensional. As you can see, the array of materials that are there, starting with nanoparticles to nanofibers to nanostructured surfaces to three-dimensional nanowire arrays or nanotube arrays. Now, the question is, how can we utilize these nanomaterials in biology? Whatever be the material origin, you can actually use it for varieties of applications in medicine. How? Basically, by interacting these varieties of nanomaterials with various biomolecules, thus developing a hybrid. And you can use it either for therapy, or for diagnosis, or for sensing, or for catalysis, etc., etc. So whatever applications you can think of, you can utilize nanomaterials in biology as well as in medicine. Such materials are what I would be calling as nanobiomaterials. And you can rationally design these nanobiomaterials for the different applications that we envisage. And it can have a specific functionality that can help you to integrate with the biological complexity. Please understand that biology is very, very complex. Now, for the specific application that we are planning to develop a nanomaterial, we have to consider that specific functionality. And we have to engineer the material in such a way that the nanobiomaterial can perform tailored functions in the body. These can be as diverse as drug delivery, to disease diagnosis, to wound healing, or we can even develop implantable devices. There are lots of biomedical implants. I will be touching upon a few of them. And we can even engineer tissues. This is the field of regenerative engineering. So all of these fields can utilize diverse kinds of nanobiomaterials. And the new word or the buzzword now is actually nanomedicine, because we are actually in an era of personalized medicine. When you say nanomedicine, we are actually talking about the medical applications of nanotechnology with materials whose size scale is of the order of 100 to 200 nanometers. We can utilize them again as diagnostic markers, both in vitro and in vivo. We can deliver drugs to site-specific locations or use them in tissue engineering and regenerative medicine. Now, what is the importance of nanomedicine? You can see that in comparison to conventional medicine, we can have a very fast diagnosis of various ailments. And the biggest advantage with nanomedicine is its precision. You can actually give precise treatments to the diseased cell alone, sparing the normal cells. You can repair tissues deep within the body, and targeting is one important aspect that is addressed by any nanomedicine, wherein we can actually conjugate any biomolecule on the surface of a nanoparticle or any nanomaterial and drive them specifically as a bullet. You can aim it at the diseased tissue. That in turn spares the normal tissues, and thus we can do away with a lot of side effects that are otherwise observed. For this reason, the global nanomedicine market is actually on the rise. Whatever be the modality that you're considering, whether it be therapy or diagnostics, and various applications that we talked about now, by utilizing either nanoparticles or nanoshells or tubes or wires, fibers, whatever, and for varieties of diseases, ranging from oncology to cardiology to infectious diseases. You can span the entire gamut of, disease field in medicine. And you can see the global nanomedicine market is actually going to cross around $1,000 billion by 2030 with a very high growth rate. So that speaks to you about the nanomedicine market. And our group at Amrita, we also have been doing extensive work in this direction. We have been working with nanoparticles for disease diagnosis, nanoparticles for drug delivery. I have been working extensively with nanofibrous materials as implantable devices. Not just that, we have also been working a lot on metallic implants and doing simple surface modification techniques to improve the performance, such as, for example, stents. Stents have been surface textured such that endothelial cells adhere to that much and perform much better in comparison to the conventional clinical cells, stents, which are drug eluting. So we have been working in all these fields. And in this particular talk, I'll be actually talking mainly about nanoparticles for drug delivery and nanofibers as implantable devices. So moving on, to develop all these nanomaterials, we have a wide variety of processing tools to make materials which are at the molecular scale, to nano or meso scale and even up to macro scales. And we can develop, complex materials also. So there are different techniques that are already in place. Molecular self-assembly, geometric self-assembly, electrospinning, photolithography, 3D bioprinting, etc., etc. Now, first, let me start with nanofibrous materials. As you all know, nanofibers is very much in use for a lot of applications, and we can synthesize them using a wide variety of techniques, of which electrospinning is one very important technique, which is a very simple technique actually, in which a polymer solution is taken in a syringe and a very high voltage is applied to that. And you can get a very random or a particular aligned geometry of fibers. And what is important in biology with these nanofibers is their scale dimension. So you can see that we can get nanofibers starting from 100 nanometer to 200, 400, 800, or even microns. I'll be just touching upon a few of them. But what's important to note is that this dimension and the size scale is actually mimicking that of the extracellular matrix which is in your human body. So the complex structure of extracellular matrix is actually mimicked by the nanofibers. And that is the reason why these cells are able to really like such kind of surfaces. So electrospinning technique has come up a long way in the nanofiber technology. You can utilize synthetic polymers ranging from, I'm sorry, just give me a minute. You can develop nanofibers from synthetic polymers like PLGA, PLA, PCl, etc., etc., as well as natural polymers like collagen, elastin, chitosan, etc. You just need to prepare a polymer solution of the right concentration and viscosity. And you'll get fibers like this, which have structures that mimic the natural extracellular matrix dimensions. Not only that, you can tune the parameters in electrospinning and get micron size fibers or nanoscale fibers, or even you can get multi-scale fibers. Whatever it is, the cells really love these fibers. You can see cells attach, they make multiple contact points. One cell makes multiple contact points with numerous fibers. On a nanofiber, it really loves the surface. But in contrast, on a microfiber, it does not spread that much. And for that reason, we can make a nano micro geometry, like what you saw in the previous slide. And you can see that the cells will actually get inside the fibrous geometry. Whereas in this case, where there are only nanofibers, the cells sit on the surface. The porosity is not too big, such that the cells can permeate or penetrate the scaffold. Whereas when you have a multi-scale scaffold, micro nano, the cells can actually get inside the structure like what you can see here. So in general, the cells love these nanofibers. So this is something which we have been understanding for quite some time. World over, people are working a lot on electrospinning for various applications. I'm taking a D route here to talk about some difficulties with conventional electrospinning. So conventional electrospinning basically uses either a static collector, which is a flat collector, or you can replace that with a rotating collector. You can get a paper-like structure, which can either contain random fibers like this, or if you rotate it on a mandrel, you can get aligned fibers. But what is the problem? There is no interlocking, there is poor packing, and hence this structure is mechanically very, very weak. So this paper-like structure to develop into a scaffold for diverse applications has limitations. So electrospun mat, which looks like this, cannot be processed into medical textiles. You know, medical textiles are a lot used in various applications, like for example, developing vascular grafts, developing wound healing mattresses, etc., etc. So you cannot use these nanofibers, though they have nano sizes, you cannot make them into medical textiles. So what our group looked into some time back was, can we think of adopting lessons from conventional textile technology? I already told you electrospinning gives you fibers. All of us have seen this. Fluffy fibers in cotton ball. What do you do with this? These fluffy fibers can be taken and bundled together and you can make yarns. Once you have a yarn, which is nothing but a thread, you can weave it, you can knit it, you can braid it. You can do any conventional textile technology technique. Your dress material is also woven. Your socks is knitted. Your woolen wares are all knitted. So you know the textile techniques are already in place. And you can make constructs of different patterns. But remember, cotton is very, very strong a material. It's a natural fiber whose strength is typically in the range of 390 to 600 megapascal for this kind of a yarn. And you increase the strength further by this bidirectional alignment and you are interlocking or interweaving. So medical textiles which are developed using yarns like this appear to be very, very strong. The question that we asked ourselves is, can we transform these fibers which go and deposit in a paper form to such kind of bundles? Yes, it took us some time to understand, but we changed the geometry of the collector. I told you the collector which was otherwise used is a flat collector. We introduced spines like this. And there you go. The fibers which collected there could be bundled together to get a thread. Now you can look at this. The thread consists of numerous fibers which are entangled together. And this is a yarn. So you get spools of yarns. You can see, you can vary the twist angle, you can vary the diameter, and you can see the cross section. See the number of fibers that are there, 80,000 odd in a yarn of diameter 300 micron. So that's very good. So we understood that if you increase the fiber packing, because of the twisting, it leads to very high lateral friction and that increases the tensile strength significantly in comparison to that of an electrospun mat. There we go. But still, the yarns are way too low in strength in comparison to our goal, which is typically 500 megapascal. So what do? We thought if you have a yarn, we can do an interlocking. That exposed to us the field of nanotextiles. And this is one of the fields that I have been investing heavily during these last 1 decade. So now, what is the importance of these nanotextiles? Or what is the importance of these yarns? It's just like any other fiber. You can actually load drugs, you can load growth factors, you can do anything. You can tune its mechanical properties. See, one fibrous yarn can be plied, braided, twisted, woven. You can do whatever you want. But remember this, you have still the fibrous geometry. So it has enhanced biocompatibility because of its ACM mimicking architecture. So all this was published and patented way back in 2018 on yarns in 2015. And from there, we have been utilizing these yarns for a variety of applications. So we developed drug-eluting sutures, we developed drug-eluting implantable fabrics, we developed drug-eluting stents, we have vascular grafts and patches. I'll just run through a few of them. Drug-eluting suture. Sutures are used in every surgical application. Drug-eluting sutures are very, very important because you have a suture and you give a medicine either intravenously or orally. Can we do away with that? Can we have the suture itself drug-eluting? But remember, mechanically, the suture has to be strong. So we devised a core sheath geometry wherein the core provides mechanical strength and the sheath contains the drug. So we have no compromise in both characteristics. It provides an enhanced therapeutic value and superior mechanical properties. So we can have any kind of such sutures developed. Now, this was all published. This is the look of the suture. You can see it looks very much like your copper wire, which has a sheath around it and there is a thread inside it. So here on the sheath, we have the drug and we tested it in vitro. Strength is not heavily compromised and we used this suture, which is drug-eluting, in an animal model, which was checked for its inflammation. So we created an inflammatory model in mice and used an anti-inflammatory drug which was loaded within the suture and put it in the dermis and looked at how fast the animal recovered. So all this was done. Once we understood that we can load drugs within these fibers, we tried to answer a lot of questions which the surgeons posed before us. So one day, when an oncosurgeon, Dr. Vijay Kumar, talked to me about this use of drug-eluting implants, he talked to me about epithelial ovarian cancer, which is actually a silent killer because it's diagnosed more so in the stage 3 and stage 4 of the disease, wherein mostly what happens is the ovaries are removed and the uterus is removed and a lot of other organs which are there. And this is the peritoneum, okay? This is the under the diaphragm. So a lot of organs are there within the peritoneum. Now, what happens is once the ovary gets the disease, the spread happens within the peritoneum. So what the surgeons now do is a cytoreductive surgery. And then they give a IV chemotherapy of platinum and taxane drug combination. But what happens is there might be some tumor cells which are residue and there can be peritoneal adhesions. And heavy dose of chemotherapy, causes a lot of toxicity issues and side effects. And ultimately, it again brings back the disease, that is disease relapse. So what the surgeons do is they open, remove all these organs, and then they give a injection of paclitaxel, that is one of the drugs, taxane drugs, and then they close the peritoneum. And then the patient is put on, a catheter, and the patient comes every week and gets injections, that is chemotherapy. So this is very cumbersome. So the doctor asked me whether you can develop something which can be put inside the peritoneum, which will slowly elute the drug. That is where, when we had finished our work on these surgical sutures. So I said yes. And I asked, sir, how long do you want the drug release to be? So he said, as long as you can, 3 months, 4 months. Oh, so we started this work wherein we loaded the drug within the fiber. That is paclitaxel was the drug. And we selected an appropriate polymer, which is polydioxanone. This is a weaving system that we have in the lab. There's a tabletop loom. It looks very much like our loom, big looms, small version. And we developed textile. You see that? We developed textiles of different packing density. I'm not showing you all the data, just a glimpse of it. So this looks very much, this lower one looks very much like the gauze, the wire gauze which you have. We check the drug release. You can see that this is tightly packed. This is loosely packed. Now we have a yarn like this. We have something like this. We have intermediate structures also. And we have a very tightly packed. Now look at the drug release in vitro. We see that very tightly packed structures do not release the drug very fast. But the loosely packed structure, which look like the gauze, release the drug very fast. And it was not very fast, but similar to that of the single yarn. So we understood, okay, we can get it. Now we put it inside the peritoneum of the mice. So what you're seeing here is a mice peritoneum into which you have put the nanotextile. So here on, I'll call this as a nanotextile. Now you see this, the drug was eluting up to 2 months in vivo in the peritoneum. Why all this happened? Because we always use degradable polymers. So the degradation of the polymer caused the drug elution. So we are there. So we got very good publications with all this, and we understood that all the organs which are there in the peritoneal cavity had drug concentration even up to 60 days. And even up till 60 days, we could detect drug concentration in the feces, because paclitaxel is one drug that gets majorly eliminated through feces. So only if the drug is present within can it get eliminated. So we understood a big point, that we are getting a sustained drug retention and release from the implant. So that was a good point. There we moved on. In collaboration with Northeastern University Professor Manzoor Ameji, we worked on the in vivo efficacy study in tumor-bearing mice. This is the bottom line. I'm not showing you all the data. Anybody interested can look through our papers. We developed the tumor model. You can see in ovarian cancer patients, mostly the tummy gets bloated up. You can see the same thing happened here because azotic fluid gets accumulated. Here, this is an untreated mice bearing tumor. And you can see this is the histological image to prove that tumor is present. Now, after 35 days of treatment, look at the same animal. There, the nanotextile was implanted and the drug eluted over time and the tumor was completely disappeared. And you can see the histology showing similarity with that of the normal naive animal. So what do we understand? We understand that the woven nanotextile which was put inside a tumor-bearing mice could also elute the drug over a sustained period and increase tumor responsiveness. So this work was patented and published in Journal of Control Release in 2019. We understand thus that we can load any drug, we can load a good concentration of the drug and develop any kind of implant. Now came the gastromedicine people for discussion. Can we actually transform a biliary stent? You know about pancreatic tumor, which is now very common. The bile duct inside our body. This is the bile duct. It gets blocked. Once the bile duct is blocked, the patient dies. Most of the cases turn out to be inoperable. This is what is called as malignant biliary obstruction. So what is done now is to insert a bare metal stent inside the bile duct and give doses of medicine intravenously. Remember one thing, the tumor is here in the bile duct or around that area, in the pancreas maybe. 1,000 milligram of gemcitabine is the clinical drug which is used intravenously. Very little of this drug reaches the bile duct. So the question was, can we actually develop a drug-eluting stent? We answered that and we developed a stent which has the thread around it with the drug which was laden, gemcitabine. So you can see gemcitabine is a highly hydrophilic drug. The polymer that we used was a hydrophobic polymer because we wanted drug elution for a long period of time. To work with hydrophilic polymers and get long-term drug release is a very difficult proposition. So we utilized a hydrophobic polymer and we tried to encapsulate a highly hydrophilic drug within that polymer. We had to do a lot of gimmicks, but we were successful in doing that. And we integrated the yarn by stitching on top of this particular SEMS. We call it self-expanding metallic stent. And there we go. We have the stent which can be deployed the same way as a normal self-expanding metallic stent. It can be put within a duodenal stent delivery device. And what is the next step? We proved it in vivo. We implanted these SEMS in porcine bile duct. So this is the bare metal stent and this is the, so what you are seeing in white here is actually the stent. I'm sorry, the yarn over the stent. And you can see the fluoroscopic image. The stent is sitting here and this is a bile duct, believe me, and this is the open stent. This is a bare stent and this is a nanotextile integrated SEMS. We did a lot of studies. We actually looked at how it behaved as a function of time. So we explanted, so you can see the SEMS sitting here. This is a bile duct and this is a gallbladder. Now look at the control stent, which is the normal stent. This is actually what happens in humans also. As a function of time, the stent completely gets blocked. See that? 3 months, 5 months. Both at 3 months and 5 months, there is totally a fibrous deposition within the stent. You can see they call it sludge. Inflammation was also pretty high as obtained from histology. Look at the nano stent. When I say nano stent, I mean the nano yarn integrated bare metal stent. See how open it is? See the histology? It was patent. Even up to 5 months, it eluted the drug gemcitabine hydrochloride. Biochemically, no changes were observed. A lot of liver function tests were done. In the bile or in the blood, we couldn't detect any drug remnant, but we could find drug remnant in the yarns that were present around the stent even after 6 months. So this was a long-term study in a large animal. Liver function tests and C-reactive protein of the animals were within the normal range, and there was drug elution to as long as 5 months. So our experiments proved the safety and efficacy of nanostents. Now we are in plans in discussion with the clinicians to take this work further towards clinical trials. Another story is that of nanotextile vascular grafts. Cardiovascular thoracic surgeons use vascular graft for bypassing. You know, vein is cut from your leg. It is called as a saphenous vein, and it can be from the internal mammary artery, and bypass is normally done. But this will work perfectly normally. But in many patients, it's very difficult to get the saphenous vein and internal mammary artery. So the best substitute is synthetic vascular graft. Synthetic vascular grafts, which are made up of PTFE or PET, which is called as polyethylene terephthalate, or poly, which is called as Dacron. All of them work for diameters greater than 6 millimeter. But all of them so far have failed at diameters less than 6 millimeter. So the question lies, can you actually develop a small diameter replacement? So we started our story here. We have the yarns. We devised a cylindrical weaving machine. Right now we don't need a fabric which is flat. We need a tube. So we need machines for that. We developed this machine in-house, and you can see we did the weaving to get a tube like this. See the length of the tube? These are conduits of diameter 4 millimeter. This is the lateral view of the same. You can see how closely packed it is. This is a fibrous yarn. This is one yarn. These are yarns which are crisscross, bidirectional alignment. And we transformed nanofibers into woven nanotextiles, and we demonstrated vascular application. So this is the SEM image of the tube. In conjunction with Professor Raimondo and Professor Sarah George from University of Bristol, he is Professor Raimondo, he is a CVTS surgeon. He implanted this in porcine carotid artery. So this material was again based on poly-L-lactic acid. Implantation was done. You can see this is the woven graft which was put together with the normal thing, and I'm not showing the videos. These are all videos, in fact. And you can see that the material was thoroughly intact, and blood flow was monitored 30 days after anastomosis. This is Doppler showing that blood is flowing through this graft material. This is ultrasound image. This is a transverse image. This is the longitudinal. You can see the textile is here, and from here is the normal vein or the artery. So through this, you can see blood flow is there, and this is a pulse wave. So everything was working perfectly fine. Last story. I'm not showing you all the data. We explanted, that is, we euthanized the animal and took out the vascular graft and cut it open and looked at what is inside. Look at the staining. This is actually what we call as end phase staining of the nanotextile graft. So what you are seeing here are cells. What cells? Endothelial cells. What is shown in blue is the nucleus of the cell, and what is shown in green is the boundary of the cell. So what we understood was that complete lumen of the vascular graft is covered with endothelial cell. And this is precisely what we require. And on the outside, we could see beautiful alignment, smooth muscle cells. And the stent worked without any problem for 3 months. That's all the study that we did so far. Now we are in a plan to move on further. The same material can also be utilized as a vascular patch, which can be used for all these septal defects. You might be familiar with atrial septal defects, ventricular septal defects. You might be familiar with the word hole in the heart. That's the common layman's language. To close that hole, we can use this material, because in contact with blood, Endothelial cells are very well attaching. Smooth muscle cells are not attaching. And this is precisely what we require. So there we are, we are able to prove that nanofibrous materials can actually go a long way in developing different kinds of implantable materials. And this is the last story with nanotextiles. Our group at Amrita has developed a bone graft substitute to address mandibular tumor or trauma management. This is a big clinical problem. You can see a patient can lose their mandibular jaw. It can be due to an accident. It can be due to tumor. Oral cancer can come and eat away this region. And you see how disfigured the patient gets. So what do patients do now? And what do the doctors do? They cut a piece of bone that is fibula. But this fibula is short in height. So they keep fibula, and on top of that, they keep something to augment that height. So vertical augmentation, that is increase the height up to the required thing. Increase of bone height is done, and then you can place implants, dental implants like this. This is what is normally done. It's a very big procedure because you have to do surgery at multiple places, because you have to get the fibula from your leg, and you have to get another part from another part of the body. So you keep it. So you can see fibula is only 1.2 centimeter, mandible is 4 centimeter. So there is always a disfiguration like this that happens. Can we address this problem? This is the problem that Dr. Manita actually took up to address. Why I am talking about it is because we developed this material together, a bone mimicking material as a graft, totally synthetic material, which was based on silica, hydroxyapatite, and gelatin. And in that, we reinforce that material with these yarns. You can see the yarns. And that conferred a very high toughness, mechanical stability, and bone regeneration potential. So all the studies were done in vitro, in vivo, small animal, large animal. Large animal we did for 6 months in pig mandible. Critical size defect of 3 by 2 by 1 centimeter cube was actually made, and you can see the graft was positioned. Without any other augmentation, just the graft was positioned. And you can see that there was complete remodeling or regeneration within 6 months. As you all are aware, we have a GMP facility that we have set up at AIMS, wherein we are preparing this material, and we call it the Nanotex bone graft. Test license application for the GMP facility has been obtained, and we manufacture this GMP class material, and we are testing it currently in patients. So this material is currently undergoing pilot clinical trial in 10 patients at Amrita Hospital. So this is a work forward that has actually taken on, and we are at this stage where we are thinking of a clinical translation. Should I move on? I have a portion on nanoparticulate materials to discuss if you are interested, or I can stop here.
Yes, ma'am, you can continue.
Okay. So far I was talking mainly about nanofibrous materials, which are developed by the technique only by electrospinning, wherein we saw that mechanically weak fibers were transformed to mechanically strong yarns and utilized for a lot of applications. Now, we have another set of materials in the nano size scale, that is nanoparticles. Nanoparticles can be developed. You can engineer nanoparticles. It can be based on polymers, or it can be based on inorganic materials, or it can be based on lipids. And you can utilize them for wide variety of applications. This is a very beautiful Nature review paper published in 2021. It speaks about diverse applications of each of these materials. So I'm going to focus on polymeric systems for this talk. We have been working on varieties of these materials for diverse applications. engineered nanoparticles can be extended for applications not only in biology but also in medicine, such as you can develop drug-loaded particles for cancer or any other drug delivery. You can use them for biomolecule detection, that is biomarkers. You can use them in cosmetics. You can use them in molecular imaging. You can use these particles for regenerative applications. You can deliver growth factor or whatever. You can use nanoparticles such as quantum dots for diagnosis or any other luminescent nanoparticle for diagnostic applications. You can develop antimicrobial drug delivery systems. You can deliver genes through them. So engineered nanoparticles can be utilized in almost all these applications. I pick one application. I talked about drug delivery. So I'm considering drug delivery as a case. I'll just show you a few things. Inflammation. This is something which all of us. So I am now inflamed. And that is the reason why I could not reach there. My legs are swollen. I cannot walk. What do I do? Disease management of this kind of a situation is routine. All of us hit somewhere. All of us fall somewhere. You have edema that develops. That is contusion, swelling. What do? Most often, non-steroidal anti-inflammatory drugs are given. NSAIDs they are called. Over the counter, you can go and buy it. Over the counter. Nearly 30 million people take NSAIDs daily worldwide. Imagine the use. 400 formulations of over 15 non-steroidal drugs are available, are marketed. 70 million prescriptions are written each year in US alone. So you can imagine the use. All of you might be familiar. Aceclofenac, diclofenac, Brufen, Voveran. Lot of drugs like this are there in the market. Doctors prescribe many of this. Basically talking about NSAIDs, it is a COX-2 inhibitor. I'm not getting into the biology. You can see there are two classes of NSAIDs, non-selective and selective. Selective, of course, will be much more effective. But most commonly used are non-selective NSAIDs, such as diclofenac, ibuprofen, ketoprofen, aspirin. All of you know that. Like this, there are several drugs. I told you, selective NSAIDs might be better. But you see, it has been retracted by FDA because it poses severe cardiovascular risk. So, amongst all these medicines, non-selective NSAIDs that we said, diclofenac happens to be one of the most commonly prescribed drug. In what all form? Either as a tablet or as a gel or as a suppository or as an injection or as a patch. You see, lot of formulations are available. But the most common is this as a drug or a pill. And now you can see extended release formulations are also available. Very good. All good so far. But what is the problem? You see this? This is ulcer. So if you take aceclofenac or diclofenac on a regular basis, you will develop gastrointestinal ulcer and it can lead to renal and hepatic toxicity. You know what? See the drug dose 100 milligram and this is prescribed 3 times a day. Why? Because the drug has very poor bioavailability. The drug gets eliminated very fast, short half-life, and very high protein binding. So most of the drug is really not available, mainly because it's highly hydrophobic. So what happens? The doctors give multiple doses. Multiple injections are also given to maintain therapeutic concentration. So we are posed with all these challenges. We have to reduce the toxicity. What should we do to do all that? We should sustain the release of the active pharmaceutical ingredient for a long duration. That only can help to improve the bioavailability. And we have to do away with so many frequent administrations, whether it's oral or intravenous. So we have to have patient compliance. What is the solution? Nano encapsulation. So we started with this work. This is a clinical problem, okay? So we understand that we are moving towards translational nanomedicine. When we think of translational nanomedicine, we are thinking about nano encapsulation. So we want a carrier. Think of a ball into which you want to put the drug. So that's a carrier. Nano carrier should have, it should be in circulation for a long time if you are intravenously injecting it. It should release the drug over a long period of time, and it should have stability. Material, just the drug will not help. You need a material. So you require excipients. Excipients are anything other than the drug. So material excipient ability, it should be non-toxic. It should be biodegradable. Its degradation product should not be toxic, and it should be excretable. And all this have to consider process scalability also. That is, it should be an easy process and it should be cost effective. Only then can we think about translational nanomedicine. We can choose from the entire matrix of materials that are there, either natural or synthetic. Synthetic has its own drawbacks. We are saying so. So in this particular study, we focused on starch. It's a very cheap material, easily available and used in varieties of forms. You see, lot of starch derivatives are there, of which hydroxyethyl starch is a commonly clinical material used as a plasma volume expander as an injection. So why not we select that? So we started with our experiments on hydroxyethyl starch to encapsulate diclofenac sodium. Just one slide of synthesis. This is hydroxyethyl starch. Remember, hydroxyethyl starch is water soluble. Starch is nothing but your kanji vellam. So you require a cross linker. So this is a cross linker. We did the reaction and we obtained cross-linked hydroxyethyl starch. We did the chemistry. We got diclofenac loaded hydroxyethyl starch. Now I told you we want it in circulation for a long period of time. So we used a stabilizer which is lecithin. Is a FDA approved stabilizer. So all the materials that we have used here are FDA approved. So the synthesis is cross-linking with precipitation. We got very beautiful nanoparticles of diclofenac. Look at that. Particles of approximately 100 nanometer to 200 nanometer size with very good stability and a high colloidal stability represented by its negative 45 millivolt zeta potential was obtained. Drug entrapment was very good. Stability was also good. Drug loading as high as 10 was obtained. See that? Release. We don't want a very long or sustained release, okay? We want to do away with the multiple injections that you do daily. It can be multiple injection or administration. So, you see, we looked at it for 72 hours. So we could get a very sustained release of the drug as long as 72. I'm not getting into all this. The drug was coming out mainly by diffusion, but at later time, it was also coupled with swelling and erosion from the polymer matrix. We published all this. We moved on to pharmacokinetics. We want to check how long this drug will be in circulation. Tail vein injection was given, bleeding was done retroorbitally, and analysis was done by HPLC. Now, I'm going to test it in animals with controls bare diclofenac and Voveran, which is a marketed clinical formulation. I use 2 doses of the drug. One is 2.5 milligram per kilogram body weight of the animal and one a high dose. We calculated it based on some formula, allometric scaling and animal equivalent dose of the human equivalent dose, 15.4 mg. So just understand that 2 doses were tried. I'm going to show you the results. First one is 2.5 mg per kg body weight. Comparison of green nano diclofenac was done with blue Voveran and red is bare drug. Bare drug gets eliminated very fast. This is intravenous, okay? So it starts from a high value and it just gets eliminated. In contrast, Voveran, which is a clinical drug, sustains itself up to 48 hours. Now, look at the green one. It sustained for a longer duration, but the concentration was very, very low. And improved circulation was obtained, but then we could not enhance it for too long. That is, therapeutic window as per EMA standards is 1.4 to 3. And we are way below that, the green one. What did we do? We PEGylated. Now, all of you should know, PEG or polyethylene glycol is a molecule which is hydrophilic, which is neutral, which is biocompatible. And this is a material that can evade all protein absorption. And that can actually result in a higher circulation. So we covered our nano-diclo formulation with PEG. And there you go. We looked at it up to 120 hours. So P and D represents pegylated nanodiclo. See the comparison? This is ND at 2.5 and this is P and D. So a much higher concentration of the drug as a function of time could be obtained and drug release could be sustained even up to 120 hours. All good. Area under the curve was substantially enhanced. 31-fold increase in mean plasma concentration was achieved. Are we done? No. I checked a higher concentration. So effect of dose was evaluated. Comparison was made. You can see green is overran, ND is blue, PND is this lavender color. Not much of a change. High concentration did not do much of a thing. Though the increased value of the concentration, maximum concentration could be achieved, we could not prolong the plasma concentration in the therapeutic window for too long. Comparison between 2.5 and 15.4. 2.5 was much better in comparison to 15.4. We studied why. It was getting biodistributed and it was getting accumulated in the organs. But see that, can we move away from 2.5 mg per kg body weight to as low as 0.4 mg per kg body weight? Which means, are we able to get a better therapy at a lower dosage? This was a question that we asked ourselves. To answer this, we did pharmacodynamics, which means efficacy. What did we do? We induced inflammation in the animal. See that? By giving a subplantar injection of carrageenan, which induces inflammation in the animal, we did that and we intravenously injected the test sample and we measured the pore thickness. Now, look at that. Pharmacodynamics 2.5 versus 15.4. Up to 96 hours, we checked edema. Edema is the swelling. How efficiently could the drug reduce the edema? So here what you have to see is how much low can it go? That is the thickness, swelling. How low can it go? See that? You can see that the green 2.5 mg per kg body weight could induce a significantly less edema over a sustained period of time. So I'm not showing you all the data. What we understood is 2.5 mg per kg showed better efficacy than higher concentration. So a better therapy was possible with lower dosage only by nanoencapsulation. We understood that biodistribution of this higher concentration was significantly different from that of the lower concentration. So what was impossible was made possible by nanoencapsulation. This work was also published. And now, this is the case of a single drug. What if you are given two drugs and you are asked to prepare a nanoparticle? So I just present a last case of dual drug delivery. Two drugs. One is paclitaxel, about which I talked earlier, and another is, this is a part of a thesis that I'm just putting forth. One is paclitaxel and another is EGCG, which is nothing but green tea extract, active pharmaceutical ingredient from green tea. Paclitaxel is a hydrophobic drug. You know, tea is hydrophilic. The question that we asked ourselves is, two different drugs, can you put in the same carrier? Same ball, can it contain both? We tried doing that. It did not work. We did a single emulsion. PLGA was capped with PVA. You can see all that. One drug got encapsulated high. The other drug, no. So we moved away. We understood that the release was also not good. We understood that encapsulation of two different drugs within a single compartment is difficult. So that made us think about a coercial system. Put one drug in one compartment, put another drug in another compartment. So I know already, I have used extensively PLGA to encapsulate paclitaxel because both are hydrophobic. Now, I have a green tea. What do I use as a carrier for green tea? That brought us to milk and tea combination. We are trying to use this old wine in a new bottle. We know milk protein will bind with green tea. It's not a covalent interaction. It's a non-covalent interaction. Very good. We cannot interact it covalently because then the drug will not release. So we did core shell nanomedicine. PLJ, one is oil phase, another is water phase. PLJ is the oil phase. PLJ is a hydrophobic polymer. Paclitaxel is a hydrophobic drug. Casein, that is your milk protein. And EGCG is your tea, water phase. See that? Beautiful PLGA particle. But you see this fellow black thing? So paclitaxel was encapsulated in a very high concentration. Again, EGCG was not encapsulated high. What do? We understand that casein has to be precipitated. So this is nothing but casein, okay? The protein casein was sitting outside, somewhere, here and there. So we understood that the protein has to be precipitated. So we changed the route from emulsion to emulsion precipitation, such that, you see this, the casein has to form a shell like this around your round PLGA. See that? Beautiful particle. PLGA containing paclitaxel and casein containing EGCG. See the particle size? 190 plus minus 12. See the encapsulation efficiency? 96%, 77%. So all well and good. In vitro, understood? We optimized a lot of parameters and all that. In vitro, you can see what is outside will come out first. So EGCG is outside, will come out first. Paclitaxel will follow it. We understood that we can do that as a function of time for a long time. And there is a burst release initially and then a sustained release. All that is understood. Whether the same will happen in vivo, we wanted to check it in animals. So the pharmacokinetics was studied. 10 milligram per kg of paclitaxel, 15 milligram per kg of EGCG was injected in rats. This is a bear drug. Bear EGCG gets eliminated within 8 hours. Bear paclitaxel also gets totally eliminated within 8 hours. In contrast, see that? See the time? This is 8 hours. Here we are talking about 375 hours. This also 375. Now look at the difference. From the shell, EGCG came out in a burst manner. That's okay. After that, it started to sustain for a long duration. After the shell was completely over, the paclitaxel burst out. Till the time, paclitaxel concentration was very low. So isn't that wonderful? Our thought was to utilize EGCG to sensitize cancer cells towards paclitaxel resistance. So our intention was to deliver this combination for breast cancer therapy, wherein we have to first deliver EGCG and have it sensitize the resistant cells and then deliver paclitaxel. And it worked beautifully. I'm not showing you the data, but the most important thing was that the drug release was within the therapeutic window. So the core shell nanomedicine displayed enhanced bioavailability, and you see the time, it was circulating for a long period of time. All that was because of the core shell geometry, wherein we could achieve sustained drug concentrations for a long time. This work was published in 2014, but later the importance of this material for breast cancer therapy was also established and published later. So I summarize. I have presented to you two different kinds of materials. One is nanofibrous materials, which can be utilized in delivering drugs, developing implants of diverse kinds, and also as metric reinforcement. Nanoparticulate materials can also be developed with tunability in drug delivery kinetics for diverse applications, for cancer, for any kind of renal diseases, for cardiovascular diseases. And the understanding is that we can lower the drug dosage and we can reduce the frequency of drug administration. So even if you go small in size, we can develop something which is strong and which is having high potential for bigger advances. Thanks to my entire team at Amrita, Professor Shanti Kumar Vinayar, our director, and my colleagues who have worked with me in all these works, all the surgeons and the clinicians at Amrita, CVTA surgeons, Dr. Praveen Verma, Dr. Rajesh, Dr. Pavitran, oncologist, Dr. Vijay Kumar, the surgical oncologist, Dr. Priya Nair, the gastromedicine specialist, and a lot of thanks goes to Dr. AKK Unni, who heads the Central Animal Facility, without which I cannot be showing you all this data. And special thanks to my international collaborators. And without the funding from all benevolent funding from all the funding agencies, all this work would not be possible. And I would not be saying all this without the strength of my MTech and PhD students. This is an earlier picture. I wanted to show you that many of them who are here have been instrumental in the work that I put up there. Thanks for your listening.
Now the session is open for asking questions.
Thank you, ma'am, for your interesting and informative talk. Ma'am, I have a doubt. Please correct me if I'm wrong. Ma'am, you have used the nanotextile for drug elution. So in that, how, ma'am, can you tell me how you have loaded the drug with this nanotextile? What may be the interaction?
So basically, what we have done is during electrospinning, just the same way as the polymer is dissolved in the solvent, the drug is dissolved in its solvent, and the polymer solution now contains the drug before electrospinning. So during electrospinning, you have the drug plus the polymer that goes, and the fibers that form will contain the drug inside, and some part of the drug will also be on the surface, which is the one that causes a burst release. So the interaction is, there is no chemical interaction per se, but there can be interaction between the drug and the polymer. It can be, it's always a non-covalent interaction. It can be hydrogen bonding. So the drug interaction can be understood based on the analysis that you do. We can do FTIR and understand what exactly is the interaction between the drug and the polymer matrix. That will vary from the polymer to polymer as the and the drug to drug. So we cannot generalize and say, but in general, the polymer encapsulates the drug, and it's done during the process of electrospinning.
Okay, ma'am. One more doubt, ma'am. That is, you said the elution is based on the biodegradation of the polymer.
Yeah.
So once the polymer is completely degraded, we have to replace the, or we have to put new implant, or
Yeah.
uh,
So right now, our intention was to get a maximum elution. And for that reason, what we have chosen are specific polymers about which we know that the degradation is long. So in some cases, we have selected, I told you, polydioxanone is actually a clinical sewage material which degrades in the time range of 4 to 6 months. So we would have a polymer that sustains itself for as long as 4 months at least. So we can choose that polymer, polydioxanone, if you want something like 4 months. We can choose PCl, polycaprolactone, as a polymer if you want a very long elution. Like, for example, the drug eluting stent, biliary stent that I was talking, we utilize PCl. And we wanted a elution as long as 6 months. So all that will depend on the choice of your polymer, the concentration of the drug that you load, the efficiency with which you can load the drug within the polymeric matrix. So how much can you load? That's an important question. So till the time the polymer is there, the drug elution will continue if the drug is loaded at a high concentration. Now, we can think of, I'm also parallelly working on matrices which can be, put inside, about origami. So I'm
yes.
thinking of something based on origami wherein, you can insert implants at later time points as well, instead of doing a totally invasive surgery. So the implants that we talked about today are the ones that will elute the drug as long as the polymer is in place. There is
Okay,
no way that you can replace it.
okay, thank you, ma'am. Thank you so much.
Thank you, Professor Deepthi, for the wonderful talk. You threw light on the various aspects of using nanomaterials for medical applications. I have a couple of basic doubts because you were touching upon the various organs where these nanotextiles are being tried out. Starting from heart or diaphragm or whatever it is. But then my question is, how would you decide which kind of polymer is to be used to make a nanotextile? Which is to be implanted at a certain, certain specific area inside the body.
Yeah.
Second doubt that I have is, something which is in line with whatever Dr. Shanti has asked. because when you load a drug into a polymer, I think we need to rule out any unwanted interactions between the polymer as well as the drug, because when it's going to be there for a longer period, let's say when we talk about sustainable release, maybe for a period of 3 months or so, we have to be sure that the drug is still in the active form, right, while it is loaded in the polymer. So what are all the parameters that we need to look into?
So, one thing that is very important is that the choice of the polymer. Firstly, when we talk about any biomedical application, we normally or anybody would actually start with FDA approved polymers. We don't take any random polymer and start. If you have clinical translation in mind, it's always better that we go with the FDA approved polymers. Now, FDA approved polymer list is many. As I said, it can be in the natural list as well as in the synthetic list. So we select polymers based on the kind of applications that we have. For example, the vascular graft that I was talking about. You should understand that we are talking about a replacement for the artery. So artery is something through which the blood will flow. So when you have a replacement for the artery, what we envisage is that the artery should remain intact as long as your replacement comes up. So your material should be something which should degrade over a long period of time. For that reason, we have selected PLLA. PLLA is one polymer, that poly-L-lactic acid, poly-L-lactide. So PLLA is a polymer that can stay on for as long as 1.5 to 2 years. So what we assume is that when we have such kind of a polymer that degrades very slowly, the interaction, and remember, whenever we are using such kind of a material for a tissue engineering application, we expect that the cells will deposit its own extracellular matrix and help to regenerate the tissue. So the kind of application that we are talking about should decide the choice of the polymer. Whereas in the case of the biliary stent, our intent was only to release the drug over a long and sustained period of time. And as you asked in the second question, the most important aspect is that the functionality of the drug should be maintained. So, for which reason we normally do not do too much of interaction per se. There is no covalent linkage between the polymer and the drug, because any covalent linkage will prohibit release. And we always look for any kind of non-covalent interaction or hydrogen bonding or hydrophobic interaction. So that depends on the drug and the polymer. So we have to select the right kind of matrix for the drug to interact, and we ensure that the drug is functional as a period of time. For example, when we look at HPLC is a characteristic of the drug. HPLC will show definite peaks corresponding to the drug and its metabolites. So what we always check in vivo is the presence of the drug as well as its metabolites. So in vivo, whenever our drug enters, whichever be the route through which you deliver the drug, there will be change of the drug from the active form to its metabolic products. So in some cases, the metabolite is actually the functional one. In some cases, the pure drug itself will be the functional one. That means the drug will not undergo significant degradation or form its metabolite. So we have to analyze all these aspects when we talk about in vivo drug delivery, and we have to substantiate all this. So in nutshell, what I wanted to say is, depending upon the drug and depending upon the polymer, we have to prove each of these aspects, and we have to show what is the kind of interaction between that specific drug and that specific polymer that we have selected. And we have to substantiate why did we select that. I hope I have answered your question.
Yeah, thank you. Thank you.
Any
Thanks
other
a lot for
questions?
your. Yeah, I have a question.
Yeah.
First of all, thanks a lot for the wonderful talk. You have talked about biliary stents onto which these nanotextiles were braided. So, was it a polymeric or metallic platform?
Platform was self-expanding metal, nitinol.
Metal, nitinol.
Yeah,
Okay.
yeah.
So whether my doubt is like whether we can use this technology to other metallic platforms so
Yeah,
that we can use as for drug elution or
yeah,
anti-lighting
very much.
agents. Yeah.
Very much.
So basically, we are braiding onto directly on metallic surface or
Yeah, yeah.
any other. Okay,
No, no, directly.
directly.
Yeah.
Okay, thank you.
I'm delighted to express our sincere gratitude for your valuable and very informative session on nanobiomaterial applications in medicine. Thank you, ma'am, for joining us.
Thank you.
We will continue the session after a tea break of 10 minutes. All of you are requested to be in this hall by 11:45.
Professor Leslie, EO, can you hear me?
Yes, I can hear you.
We cannot hear you.
Can you hear me now?
Yeah, we can't hear you. You're not muted, as I see.
Hello, can you hear me? Hmm. Can you hear me?
No, I see. Can you turn on your video?
Can
Yes, I can see you, but I cannot hear you.
okay.
I don't think you're muted. I see that
No,
it's
I'm not muted.
maybe you can try logging out and then coming back in.
Can you hear me? No. Hello, can you hear me?
I hear you.
Hi, can you hear me?
No, again, it's the same thing, I think.
Same
We
thing.
cannot hear you for some reason.
Give me.
Try. Okay. Is it muted? You see anywhere?
Can you hear me?
Why? Right again.
Can you hear me now? Hello.
Try to make one.
Can you hear me? Hello. Can you hear me? Can you hear me? Hello.
See that all the settings are open. It's okay. We have 5 minutes. just had a tea break. Can you try to speak now?
Yeah. Can you
Yeah.
hear me?
Yes, now it
Ah,
is audible.
okay.
Yeah. I just used the old trick, like I turned off all the permissions and then turned them on. So it worked. Okay, I think we will start in maybe 2 more minutes. We
Sure.
have students
Yep.
coming in. We had a tea break. Then
Okay.
so we'll have an introduction and then we can start. Talk.
Yep.
Thank you. Thank you much.
Let us continue the session. Now, I would like to invite Dr. Rajita Mall, Assistant Professor, Department of Chemistry, Amrita School of Physical Sciences, to welcome and introduce Professor Leslie Eo, Professor, Macro and Nanophysics Research Laboratory, Royal Melbourne Institute of Technology, Australia.
Good morning and welcome all to the third keynote talk on today's forenoon session. It is indeed great pleasure for me to introduce Professor Leslie Eo to ICMSC 2023. Dr. Leslie Eo is a distinguished professor of Micro and Nanophysics Research Laboratory, School of Engineering, Royal Melbourne Institute of Technology, Melbourne, Australia. He received his PhD from Imperial College London in 2002, for which he was awarded the Detley Newitt Provis Prize for Computational or Theoretical Thesis of Outstanding Merit. Prior to joining RMIT, he was a mathematical modeler at Detmos Veritas, UK, and a postdoctoral research associate in the Department of Chemical and Biomolecular Engineering at the University of Notre Dame, USA, after which he commenced a faculty position at Monash University. In addition, he also held the Australian Research Fellowship and Australian Research Council Future Fellowship from 2009 to 2017. Dr. Eo was the recipient of the 2007 Young Tall Poppy Science Award from the Australian Institute of Policy and Science in recognition of the achievements of outstanding young researchers in the sciences, including physical, biomedical, applied sciences, engineering, and technology. Dr. Eo's current research interests are centered around nonlinear interactions of high frequency sound waves and matter for diverse applications that span nanomedicine and drug delivery, biosensing and point of care diagnostics, tissue engineering and mechanobiology, and sonochemical material synthesis, manipulation, and processing. With this brief introduction, on behalf of the organizing committee, I welcome you, sir, to ICMSC 2023 to deliver the talk on the topic high frequency nano electromechanical interactions between sound and matter, a new method for the synthesis, processing, and manipulation of two-dimensional and bulk crystals. Over to you, sir.
Thank you. Let me just share my screen. All right. So I hope you can hear me. Thank you very much for the kind invitation from Professor Kukani. I'm very pleased to be able to share my research with you, and thank you for your time. I guess this is afternoon or late morning in India. Um, all right, so this is where I am at the moment. If you've never been, it's a lovely place, but it's far away from everywhere. So Melbourne has been home for me for, I guess, the past 17 years. And yeah, we're located in right at the bottom, the southeast corner of Australia, and I guess they call it down under because well, someone said that it's the closest place you can get to hell without being burnt, right? So, but you know, if you can see from the pictures, hell can be quite nice. All right, so these are the people who do the real work. I just get the pleasure of telling you all about it. So we've got a team of very talented PhD students and postdocs, and also former group members. And we've been funded, very fortunate to be funded by various sources, including the Australian Research Council and the National Health and Medical Research Council. Right, and then the collaborators I have for this work, there are quite a few of them in the 2D material space, the MOF space, and also sonochemistry and crystallization. Right, this slide probably summarizes all the work in our lab that we've been doing for the past 15 years. Central to all of the different themes that we do is what's known as these sound waves, right? I want you to just remember a few magic numbers for me. And as you go along, just keep these in mind, right? So the sound waves, and I'll tell you a bit more about this. The sound waves that we play around with are 10 megahertz order, okay? And that translates into wavelengths of about 100 microns. Okay, and I'll tell you about the sound waves in the next slide or two. I guess when we first started, there's nobody crazy enough to couple these sound waves at high frequencies into fluids. There's been a long-standing, I guess, pedigree of research that has gone on with using low frequency sound waves. And when I say low frequency, I mean anything up to a megahertz. So typically most people play around with hertz or ultrasound at best at 1 kilohertz, 10 kilohertz, 100 kilohertz. Nobody's pushed it beyond into the megahertz, right? And this is key because when we started playing around with these high frequency sound waves, we see all kinds of interesting phenomena that is not seen at low frequency or lower frequencies. And so we scratch our head for a long time because the phenomena that we see can't be explained by classical theories. Then there's quite a few esteemed people from Rayleigh to Faraday that have come up with all these very robust theories, but they don't work at high frequencies, or at least they can't explain the phenomena that we see. So we spend a lot of time pulling all our hair out trying to explain them, and then that was the first 10 years of trying to at least explicate some of the things that we see and also translate them into real-world microfluidic devices for point-of-care diagnostics, biosensing, and drug delivery. I think we sort of understand it a lot more, and the key is that at these high frequencies, everything becomes very non-linear. And that's why it's different, and that's why the theories, the classical theories, which are predominantly linearized, they can't explain what we see. And then I guess we got bored. And so in the past 5 years, we started coupling the same sound waves into materials, both nanomaterials in the 2D space and also bulk materials. And just like the fluids, again, we see all kinds of new phenomena. I hope to tell you some of these things. Same thing with the cells and biomolecules and tissues. That's something we've been playing around with in the mechanobiology space as well. But that's a story for another day, right? I think that the very disparate length scales. Okay, so I've told you that these sound waves are 10 megahertz and they're 100 micron wavelengths. What I want you to bear in mind is that these are a lot longer than the molecules that we manipulate, right? There are about 5-6 orders of magnitude difference between 100 microns and, for example, the nanometer scales of the 2D crystals and the bulk crystals, right? So this very disparate length scales, it doesn't make sense, at least on the a very prima facie kind of view, to think that you've got these long wavelengths and yet you're able to manipulate at molecular scale. But yet this is something I'm going to show you. That's what's happening, or at least we think that's what's happening. It's an open space, so we don't understand everything. I hope that the clever people in this room would at least help us to try to piece together some of this the phenomena that we see, or at least the mechanisms behind the phenomena that we see. Okay, so I promised to tell you about the sound waves. These are unlike conventional sound waves, like how I'm talking to you. The sound goes everywhere. It's a bulk phenomena. The sound waves that we play around with are localized on the surface. They're called surface acoustic waves, right? As far as you're concerned, you can think of them like nanoscale earthquakes. All right, so the amplitude of these sound waves are about 10 nanometers. Okay, but the wavelengths, like I told you, they're 100 microns, 10 nanometers in amplitude. Okay, 10 megahertz in frequency. Now, you use these surface acoustic waves, or what we call SAW, every day of your lives, but you probably don't realize it, because your mobile phone has 4 or 5 of these devices, and they've been used for signal filtering and telecommunications for about 60-70 years now, right? So it's in your mobile phone, these SAW chips, right? Some touch screens also use these surface acoustic waves to detect where you put your finger on. So it's actually quite well used, although not very well known. So we make them by patterning these devices, right? And they're made of a piezoelectric material. So if you're not familiar, piezoelectric materials convert electrical energy to mechanical motion, or vice versa. So, and what we do is we pattern these finger-like electrodes. They're called interdigital transducers, or IDTs. These are just fingers of of metal strips, right? And we pattern them via photolithography onto the piezoelectric chip, right? And you can see we do this on a 4-inch wafer. You can do it 6-inch, 8-inch wafers, and you can mass produce them. How do these earthquakes get generated? Well, when you put an AC field at the resonant frequency, and the resonant frequency, or the frequency of these sound waves, and I told you they're 10 megahertz, they're set by the gap and width of these fingers, right? And typically they're about 100 micron order, commensurate with the wavelengths. So you put an AC field at 10 megahertz onto these electrodes, just like the shifting of tectonic plates gives rise to an earthquake. These fingers vibrate back and forth because this is a piezoelectric material, right? And so they generate these nano earthquakes. So that's essentially what these are. All right. There's a bit of nuance to it, but I won't go into this. There's also some interesting space in the when you match the wavelength and the thickness of the material. of this chip, right? So it's not a pure surface wave, but it's a hybrid wave that we've discovered, right? A new class of sound waves that also behave like these surface waves, but they're not like the conventional bulk waves that you see, right? So these hybrid surface bulk and bulk waves, well, for lack of a better name, we call them surface reflected bulk waves. On hindsight, not sure whether that was a great name, but we're stuck with that. They also behave like these surface acoustic waves. All right, so I'm going to talk about them interchangeably. But the key to note is that everything's localized on the surface. There are these nanoscale earthquakes that are very different from conventional ultrasound or conventional sound waves, as it were. Okay, so anyway, back to this slide. I'm gonna just focus the rest of this talk on the material space. I'm gonna start with some 2D crystals, and if I have time, I'll tell you about the morph work that we've done. Okay, so the other space that has been, there's quite a history to it, it's not new, is sonochemistry, right? The use of sound waves to do chemistry and materials processing, right? Again, these conventional sonochemistry has typically been in the kilohertz to up to megahertz range, okay? So again, these are very linear, and the way sonochemistry, or the predominant mechanism by which the chemistry is done by the sound wave irradiation, is through cavitation. Okay, and as you know, cavitation is this rapid implosion of bubbles, right, at very, very fast time scales. And when you have this implosion, you've got really high temperatures, really high pressures, 10,000, more than 10,000 Kelvin, more than a gigapascal. And that energy is typically used to drive chemical reactions or, to materials manipulation, right? However, at the frequencies we play around with, cavitation is pretty much non-existent. Okay, and that's because as you go up in frequency, you need more and more energy to create cavitation, right? And we don't, because our devices are so efficient, much more efficient than conventional ultrasound, we don't see cavitation at all. We drive things at less than a watt, sometimes even milliwatts, whereas with ultrasound, it's tens of watts or 100 watts, all right? So cavitation is non-existent. So what's the predominant mechanism? Well, I'm gonna just give you a hint, but I want you to keep that in mind throughout the rest of this talk. It's because it's not cavitation. What is it? Well, let's go back to what's a piezoelectric material. A piezoelectric material is an electromechanically coupled material. So you've got a electric field that you apply that gives you mechanical strength. Okay, so you got a field, electric field, and a mechanical field. Okay, historically, because the mechanical field is so strong, all right, and I'll give you an example. Okay, these waves, this surface acoustic waves, the nano earthquakes that I've told you about, right? They're 10 nanometers in amplitude, I've mentioned to you. Now, it's 10 megahertz in frequency. So if I sit on the surface, I'm going up and down in 10 nanometers, 10 million times a second. If I tell you the velocity is about a meter per second, what's the acceleration? Okay, it's physics 101. Okay, so the velocity divided by time, or the velocity times frequency, 1 meter per second times 10 million times per second, it's 10 million Gs, right? So you got an incredible amount of surface acceleration over 10 nanometers, right? So it's not hard to imagine that mechanical stresses can drive a lot of some of these effects, right? But there have been a lot of phenomena, and I'll talk you to some of these things,
that cannot be explained just by mechanical stress alone. And so recently we've been thinking more, we've changed our thought that more and more so that the electric field can also play a role. Okay, so the electric field is coupled to that wave, and it leaks out, or there's an evanescent field into the fluid above it, or any any sample, whether it's the material or the fluid, that can drive a lot of interesting effects from static and dynamic charging. We can do charge transfer, we can do polarization, and it's all non-linear because it happens at about 10 megahertz, or 10 million times a second. So you don't have time to charge up or discharge the double layer fully, right? So much so that we can generate free radicals in and dissociate pure water. We can split water through and generate free radicals without cavitation. And recently what we found is that not only can we split water, we can also because that water is tetrahedrally coordinated, right? We can break those tetrahedral bonds to create free water. And in this case, it was more for electrolysis, or in the water splitting setup, so that these free water molecules can more readily access the surface, so much so that when we do hydrogen evolution, we get about 14 times more efficiency, right? Or current density. So now the puzzling thing to me is, and this is where I think like I said, we don't have any answers to at the moment, is how do these break bonds, right? To break bonds is you need quite a lot of energy, yet we're pumping less than a watt into these systems, right? So it's still an open question how the electric field drives some of these bond breaking, right? The evanescent electric field. We've got some ideas and we tried to put in the papers, but I think there's still some way to go in trying to understand these systems. But the interesting thing is that Tim Mason was until very recently professor at Coventry University in the United Kingdom, and he's a big guru in sonochemistry, and the former editor-in-chief of the journal Ultrasonics Sonochemistry, which is the premier journal for sonochemistry. So before he retired, and this was back in 2019, when we were still, we were beginning to publish our work, he actually put out an opinion piece, because nobody ever, thought about any other mechanism other than cavitation to drive, sonochemistry, or at least the dominant mechanism. And he put out this opinion paper saying, can sonochemistry take place in the absence of cavitation, right? And interestingly enough, despite being this big guru of the sonochemistry field, he actually got a lot of negative comments about this, because nobody in that community believed that you can actually do sonochemistry without cavitation. And yet, we're beginning to see a lot of these things, and we're publishing at the same time some of our work saying the same. So well, at least if nothing else, this tells you about the vision, or at least the insight that Tim had at least in the courage to stand up before a very doubtful community. All right, so it's this combination of the mechanical and electric field that I want you to see. I mean, we see a lot of different effects. I don't have time to tell you all about them. We can de-agglomerate carbon nanotube bundles. Okay, I'll talk a bit about the 2D materials where we can manipulate band gaps. We can do quasi-particle ionization. We can exfoliate them, and that's part of the talk. And then with these crystallization of bulk materials like the MOFs, I'll tell you, I would hope to have time to tell you about as well. Water splitting, I've briefly mentioned, and hydrogen evolution as well. Okay, so with the 2D materials, let's just give you a bit of insight into some phenomena. The 2D materials that I'm going to tell you about is these transition metal dichalcogenides. Some of you would probably be well familiar with them. And I had a very talented postdoc, Hema Ahmed, that led this work, and my collaborator Amgad Rez, together with Kurosh Kalantazadeh at the University of New South Wales. We published this work back in 2018. So the 2D TMDs, or the transition metal dichalcogenides, I mean, some of you would know, they have, have properties similar to graphene, right? The carrier mobility, the optical absorption, but unlike graphene, they're semiconducting, right? They have this direct band gap when they're in 2D form. When they're in bulk form, they are indirect. But that makes them very ideal for optoelectronics and transistors, right? And the traditional way that people exfoliate them is through these either bottom-up approaches like CVD or MBE, which is very, very costly and cumbersome, wafer scale processing. There are only a few substrates you can grow the material on. So most people do exfoliation through mechanical shear, through sonication, right? But they need to use these solvents as well to do the intercalation, which compromises the crystal quality, and it's a very long process. Now, what we do, okay, is we nebulize. We use the surface acoustic wave, all right, and you can see the chip. Well, you can probably see part of the chip here. It's immersed into this solution, and because the accelerations are 10 million Gs, all right, you get it instantly nebulizes the fluid, creates aerosol droplets, micron scale aerosol droplets. And what we do is we wick in a solution. This wick could be just tissue paper or whatever, and the acoustic wave draws the liquid through this wick. And you can see a lot of, well, you probably can't see it, but there's a lot of streaming in the meniscus, and then behind it, in this trailing film, you get this nebulization occurring, the aerosol drops. So this solution is a suspension really of bulk. In this case, it's molybdenum disulfide, which is the TMD. Right, it's in bulk, so many layers, large chunks of them, and then we nebulize them and we collect them on this plate and we examine them. Okay, and if you look at the AFM, okay, so whether it's molybdenum disulfide or tungsten disulfide, you see, well, a couple of things. You see that they become a lot smaller and thinner, right? The height is on the order of a few nanometers, and the length scale or the lateral dimensions on the order 10 nanometers here. And you see that in the TEM as well. Okay, and if you look at the diffraction, it's still the material that we put in. But what's interesting, and I want you to take note of this, is that when we examine how many layers of these flakes, they are actually, you see, the even odd asymmetry. All right, so you got the odd layers not being the same as the even layers. All right, so which was very puzzling to us. But there was a paper by Zhongling Wang in Nature, I think it was 2005, that actually said that TMDs are piezoelectric when they are in odd layers because of the broken central symmetry. So 1, 3, 5 layers, if you got monolayer, 3-layer, or 5-layer materials, you have it's piezoelectric. If you have 2, 4, and 6 because of the central symmetry, you have no piezoelectricity. So that gives us a clue, at least, that somehow the piezoelectric of the material comes into play. So what we thought about was maybe there's a two-step process, and I'll explain why we think it that way. But perhaps, you know, in the first step, you have this shearing, all right? Because I've shown you already that, you know, there's a lot of fluid motion, and so there's the shearing of the material that causes it to delaminate somewhat. Okay, and that shear stress is quite high. All right. But it can only go so far, and I've called this, you know, intermediate step, you know, let's call it length scale LS and HS. Just bear that in mind. And then after that, piezoelectricity takes over, okay, and cleaves the material into thinner and smaller flakes. Okay. Why do we think this is happening? Okay, so I've already told you that, you know, piezoelectricity is only inherent in non-central symmetric materials, such as the transition metal dichalcogenides, but only when they're in odd number of layers. Okay. When they're even number of layers, or if this material is central symmetric like graphite, they're non-piezoelectric. And so we repeated the experiments with graphite, and we couldn't get graphene, right? We can only get large flakes, okay, on the order of 100 nanometers and many layers, okay, about 10 nanometers, which is, you know, quite a few atomic layers, right? So it can only go through this first step of mechanical shear delamination. There's no further cleaving of the material. Further evidence for this is when we go back to the TMDs and we screen out the electric field. Okay, we can do this by putting a gold layer onto the piezoelectric chip to short out the electric field. And so if you look at this case, where there's no electric field, you see the same. You see, you know, 100 nano, it's bimodal, but you see 100 nanometer lateral dimension flakes, many layers, right? And as we increase the electric field, you can see that they begin to, you know, this bimodal distribution in the lateral dimension, they more and more lateral flakes, you know, get cleaved into smaller and smaller dimension flakes. And more importantly, the many layers become fewer layers and predominantly monolayer. But again, you see this broken or you know, asymmetry, even odd asymmetry, and that's because, you know, when they have more their odd layers, they become more piezoelectric, so they tend to get exfoliated more. So the 5 becomes 3, and so the 5 depletes, the 3 becomes less and becomes the monolayer, where the 2, 4, and 6 they stop there. Okay, so that's the mechanism we think is happening. And if you do we try to do DFT calculations as well. The simulations also can show that you get these even odd asymmetry in the number of layers. Okay, and then the rest of them, that was fun and games because it's a nebulized aerosol form. You know, you can think about spraying and spray coating these materials as electrodes, patternable electrodes, and things like that. And because you saw the nebulization, it comes out so fast. You've got hundreds of millions of these droplets. Then you can do patterning very quickly, and you know the devices are very low cost, right? Because you know through mass fabrication, mass nanofabrication, you can make lots of them very cheaply, less than $1 a device. So you can do high throughput through massive parallelization. Okay. Interestingly, if you keep if you nebulize them, and we did this in a Falcon tube, you nebulize and you let them condense, and you nebulize again and condense again, and do it over many cycles, you actually break them further into quantum dots, right? They seem to they seem to be, a lot of them in monolayer form as well. But that's all I'm going to say about that work, because I'm running out of time. The other thing I wanted to say very briefly is we can also do exfoliation for MXenes, right? So MXenes, some of you will know, they're 2D metal transition metal carbides and nitrides. All right, and this is the chemical formula for them. They're very, very hot at the moment because they have very very good electronic properties and the highest capacitance for a 2D material. So that's it's a material that's receiving a lot of interest at the moment. But in order to create these 2D or at least monolayer flakes, you need to because they come in these intercalated with the aluminum layers, and so you need to do HF to etch out the aluminum and then delaminate them. All right, so it's selective etching of this aluminum layer, which is very well, HF is not very friendly, and the process is also, it takes days and it's quite laborious. So we did the same thing. All right, and this was together with our collaborators at Linköping University in Sweden, Johanna Rosen. But in this case, it's a slightly different mechanism. We think that because this is not a piezoelectric material, so something else is driving the exfoliation, right? In this case, we think it's the free radicals that come into play, because we do not need HF. We just use lithium fluoride and not HF. And we think that what's happening is we generate free radicals somehow through that electric field, that evanescent electric field that I told you about, right? That then combines with the lithium fluoride in situ to create localized HF that then does the selective etching, right? And we can, well, without going to more detail because of time, we can create these 1 micron large monolayer sheets that have that are flexible, can be made into flexible electrodes, and can have the comparable electrochemical and capacitive charging mechanisms as what would one expect of MXenes. Right. Again, we can also do the cycling, the nebulization and condensation to drive or to synthesize MXene quantum dots. Interestingly, the quantum dots that we see are very pristine, or at least they have low oxidative states compared to if you do hydrothermal synthesis. So with hydrothermal synthesis, actually you don't make a lot of MXenes, you make a lot of TiO2, right? Because of the oxidation, about 84% is TiO2. We see a lot less, about 14%, which is close to the pristine value anyway. Right, so that's interesting. I don't know why as yet we do this, but one hint can, well, that was simultaneously during synthesis of the quantum dots. If we actually put oxidized MXenes onto the device, this is not nebulization. We're just putting them there under gentle vibration, and only for a minute, right? We can actually restore oxidized MXenes, right? So it's a good way of, I guess, I think what we're doing is we're kicking off the oxides, the oxide layer. And not only that, we can actually recover. So this is the I guess spent MXene or oxidized MXene. You get a deterioration of the performance. In this case, the electrochemical performance or capacitance. We can actually restore them back to their almost pristine state, right? So in fact, up to about 98% of the value, all in just 1 minute. So that's interesting way of, I guess, recovering used material, especially in these batteries or something like that. Okay, so for the rest of the time, I think I've got probably 15 minutes or so, I'll tell you about the bulk crystals that we've been playing with, more specifically the metal organic frameworks. And I presume this is probably not new to most of you anyway. So metal organic frameworks are these crystalline coordination networks of metal centers joined with these organic ligands. And the interesting thing about them is that, well, you got these building blocks that you can build up into 3D crystals that have a very large surface area and porosity, and that's why they're so I guess so so hot at the moment. And they're also very structurally diverse. You can combine different metals and different organic ligands and build up a whole library of combinations of different materials for different applications, from catalysis to drug delivery to sensing and gas separation. So what I was going to just briefly mention, we have different ways of doing crystallization. We can use, or using the acoustic waves, we can drive microcentrifugation, we can drive nebulization like you saw before as well. And they give you slightly different results. Okay, so here's again, you can see my postdoc, former postdoc Hema Ahmed, was very productive in her time with us. So she came up with this method of driving crystallization of these MOFs using the acoustics as well. And the experiment is just simple. Okay, so here we just put a drop of the MOF precursors, a sessile drop, onto the chip itself. So that's the chip. We just put them on and we drive a centrifugation flow. And the way we do this is we offset the electrodes. Okay, so you can see this, we use one on this side and one on this side. And so the sound waves will come onto one side of the drop, and from this side it will go that way. And that, because of that broken symmetry, you can drive a rotation. Okay, and that's what you're seeing in this these videos here. Okay, so it's just sort of, think of it about it's like a centrifuge but on the micro scale, right? We do this for 5 minutes. This is HCAS. This is a copper-based MOF, if for those of you who are not familiar. And the control to this is slow solvent evaporation. So without the acoustics, we just leave it there to for the solvent to evaporate, and they crystallize anyway. Okay, and so if you look at the XRD pattern, well, first of all, maybe let's look at these as the images of the crystals themselves. You can see that with the control, they're quite polydispersed, they're quite large, and as you increase the power, the acoustic, the input power of the acoustics, and so if you do that, you create a more intense centrifugation flow. Right, the crystals that you get, the MOF crystals, become more and more uniformly uniform in size and distribution, right? And they become smaller in crystallite size as well. Okay, and then we think it's because of the turbulence that we generate within these turbulent convection that creates little mixing eddies that sets the length scale for the crystals. And why do we think so? We look at the particle diameters, and you can see that they scale very nicely with the streaming velocity, or the centrifugation velocity, to a -3/4 power, which is actually the if you do fluid mechanics, you will know that this is a what's known as the Kolmogorov length scale, which is associated with the mixing eddies or the mixing vortices, those eddy sizes. And it's a very well-known law of turbulent mixing. Right. But what's more interesting is that if you look at the XRD patterns, okay, as we go up in power, you see increasing orientation, right? So there's very little orientational preference in the control. But if you look at, say, this last case here, you see highly aligned the crystal planes. 111, 222, 333, 444, 555. These are out of plane orientations. So that was really interesting to us. And we're doing nothing. We're just, just centrifuging these as the crystallization occurs. So why is that? And that was very puzzling because, like I said, there's a very disparate, I guess, a very big difference between the length scales here. Remember, I told you the sound waves are 100 microns, right? And yet these molecules, well, molecular length scales, right? 4, 5, 6 orders of magnitude difference. How are we ordering molecules with these very, very long sound waves, which was really puzzling. To me, the best analogy I can think of is driving a truck. Okay, I see the sound waves as like a brute force method, right? So it's like driving a truck and you smash into these Lego bricks, right? And they stack up on top of each other. That's the analogy I can think of this, what's happening here, right? So to try to piece together maybe a plausible mechanism, well, here's what we think is happening, right? So when you have slow solvent of evaporation, this is the control case, okay? So what happens when you have evaporation? Well, the evaporation, because of this, you got more evaporation closer to the edges of the drop compared to the bulk of the drop, it drives a convective cell or convective flow here that drives all the solute to the contact lines of the drop. All right. So this is just pure evaporation, and this happens for everything. Okay, so much so that this is a well-known effect called the coffee ring stain. All right, and you can see that here as the drop evaporates. It's blue because this is a copper-based moth. Copper is blue, right? So you can see they all it begins to crystallize more at the edges. And this is the same with your coffee cups and things like that. Why there's this well-known coffee ring effect? Okay, and that's because of convective flow driving the solid molecules to the contact line where they are pinned and form these rings. Okay, and it's a diffusion-dominated transport, too slow to enhance local solute concentration behind the driving front or the contact line. So because of these weak molecular interactions, right, you get these molecules insufficient to drive any meaningful long-range ordering of the crystal. Okay, whereas when we've got this centrifugation flow, we've got this turbulent convection, right? We're driving a lot of things. We're smoothing out, I guess, this coffee ring stain so that it doesn't just happen at the contact lines. And you can see, we don't, well, at least you can smear out this coffee ring stain more uniformly, and you build up these monolayer stacks, okay? And then we think that it's the evanescent electric field from the underlying surface acoustic wave, because it's because of the electromechanical coupling arising from the piezoelectric material that drives, that induces these dipoles to align, right, and stack. That's the best thing I can think of. Here's some evidence for it. All right, so with the surface acoustic wave I told you about, all right, we generate it using lithium niobate, which is the piezoelectric material. Now, lithium niobate is very unique. It's a single crystal piezoelectric material, but it gives you a Rayleigh wave, or that earthquake that I told you. All right. So the polarization of the wave is longitudinal. Sorry, it's out of plane. It's transversely polarized. Okay. So it's this earthquake that you saw before. All right. But you can actually change to a different piezoelectric material called lithium tantalate. And because of its different polarization, now it's in plane. So it's not like this earthquake. It's actually like I guess it's what's called a shear horizontal wave, right? So it's in plane in the piezoelectric material itself, horizontally polarized rather than the transverse polarization here. And the electric field is also, in that same plane. If you look at the crystals, the H-cast crystals that we generate, instead of 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, we have 100, 200, 400, right? So now the molecular orientation is in the other direction. And that's because, the electric field is also in, the polarization is in plane, all right? So that's why we think that the electric field is playing a role. And then the rest of the thing is just showing the morphs are useful. And so here we do BET and show its porosity, and that's actually a bit higher than the bulk H-cast that you can conventionally make or buy. But what's interesting is that, well, if you work with morphs, right, that once you crystallize the morph, you have to activate it. And activation means to remove the solvent out of its pores, because if the solvent's trapped in the solvent molecules are trapped in the pores, it's not useful, right? The pores are blocked. So you need to do some kind of post-synthesis activation step. Whereas when we synthesize our morphs, they are simultaneously activated. We don't need to get this these adsorption isotherms. They're not done with any further activation step. And that was curious to us too. It may be that because of the vibration, we're squeezing the solvent out of the pores, but we have no way of, well, at least at the moment, to try to put some evidence to that. It's not just H-cast. We can also do different morphs, like for example the mills or the iron-based morphs, and again we see the orientation, right? So in some ways it's a facile, and well, we like to think environmentally friendly because we don't use organic solvents. We have very low energy to create highly oriented and simultaneous morphs. If we nebulize, we can also get, in fact, in this case, this is also the same precursors, copper and BTC, to make H-cast. But in this case, if we nebulize, we don't get the conventional H-cast, right? The cubic structures of the that H-cast is known for. In fact, we get a different morphology, these like 2D like rods, and in fact, it's a new structure. Okay, so it doesn't have the conventional cubic structure, the FM3M like H-cast. We get a different monoclinic structure, a P21N space group. And the interesting thing about this structure is that the copper molecules, or the copper atoms, are actually exposed on the surface of the morph. And this is very useful, or we think it's useful, because the problem with morphs is that they typically, a lot of it is non-conductive, because the metal atoms are embedded. For example, here they're embedded in the 3D structure of the morph. They're embedded internally within the 3D structure of the morph. Now, if you make it 2D and the copper atoms are exposed on the surface, then it becomes a lot more conductive. And we show, for example, that we can get about 100 times more higher conductivity than conventional HCAS. That's all I'm going to say because of time. We can also, because it's copper exposed onto these 2D kind of structures, and you know copper is antimicrobial, we can also use that to kill pathogens. And we showed the broad spectrum capability of this, not only with bacteria, but also with fungi and also with viruses. Okay, so with that, I'm going to finish off probably the last, maybe, I don't know whether I have time. I guess I'm really out of time. Okay, I'll just mention this briefly. We can also do the nebulization to actually create defects in the morph, right? So this was a work done by a PhD student, Emily Masahood, quite recently. And we exposed the, in this case, it was ZIF8, okay, to hours of this nebulization. And you can see that as it, after 1 hour, we examine the moss and we get the pores to expand. There's some slight expansion. But after 3 hours, we can actually break the linkers. And so you get this dangling linker defect, and at 12 hours, the whole linker goes missing. Okay, and we showed this useful for solvent-assisted ligand exchange. But because of time, I guess I'm gonna probably end here. So let me just conclude this talk because I'll jump all the rest of the slides. So I hope that I have showed you, you know, or at least some interesting phenomena, if nothing else, when we couple these high frequency 10 megahertz order, you know, sound waves into these different materials, whether it's 2D or 3D, and you saw the different phenomena, whether it's the exfoliation or the crystallization. You see very interesting effects arising out of what we believe is the combination or the coupling between the electric field and the mechanical field, right? I didn't have time to talk about the rest of the things, but you know, if you're interested, you know, we've published a review on this, where we talk about the other things like static and dynamic charging. We can and do charge injection as well, charge transfer. We've seen polarization effects and these charge generation effects. So with that, I think I'm going to stop here and take any questions. Thank you very much for your attention.
Thank you, sir.
Thank you, sir.
Now the session is open for asking questions.
Hello, thank you so much, sir, for the interesting talk on sonochemistry. Yeah, my query is, how can we apply the sonochemistry for the sensing of biomolecules? Can you please comment on that?
For sensing. Okay, so this is a whole different field, right? It's not sonochemistry. I presume you're talking about the sound. How can we apply these sound waves to do biosensing?